Hi, welcome to the Geospatial Analysis for Cancer Control and Prevention practical exercises. My name's Hari, and I'll be leading these exercises in using R for geospatial analysis. Today's topic is with vector data. And so the goal here is going to be to use the R programming environment to perform geospatial analysis. And in order to prepare this lab exercise today, we've drawn from a number of really amazing resources in using R for geospatial analysis applications. And you can find some references to these in the bottom of this document. So please do take a look when you have time. For today's exercise, we're going to be using the cancer cohort database from the MapGam package. And this is a package in R to do some spatial analytic procedures developed by Veronica Vera and colleagues. We wanted to find a sample epidemiologic database to motivate some of the exercises that we would be doing that are similar to some of the types of data that you may find yourself working with in your respective work in oncology research or cancer research. So this is a simulated database of 5,000 ovarian cancer cases, and it's modeled off of an existing cohort study where time to mortality is being evaluated. For our purposes, we'll just look at the event code for dead or alive, and we'll show how to do some very simple analyses with that. And so the CA data set is called that because these ovarian cancer cases are based in California. These simulated cases are based in California, and it has 6 data elements and variables: time to the event. It has an event code: 1 equal dead, 0 equal censored, X corresponding to latitude, Y corresponding to longitude, age in years, and then insurance status. So this looks fairly standard. It looks like one of the epidemiologic databases that you yourself may be working with. The second piece of data that we want to use for this exercise is socioeconomic data derived from the United States Census. And so the census is conducted every 10 years in the US and captures a lot of socioeconomic information related to income, education, demographic information like age and race. And so it's a very powerful resource for doing geospatial analysis. And so we wanted to, through this exercise, show you some of the tools that you can use to quickly pull census data into your epidemiologic studies. So to do that, we'll be using the tidycensus package developed by Kyle Walker. He has actually a whole book now, that an online book on using this package and working with census data. And that's all, again, the link to that is in the bottom of this document. And so if you're interested in learning more, highly encourage you to take a look. For our purposes, we'll be using the 2000 census data at tract level for the state of California. And we're going to be linking these 2000 decennial census data to the residential addresses that are in the simulated ovarian cancer cohort. For our socioeconomic measures, for this exercise, we focused on just 3: median household income, median home value, and percent poverty. And so we'll show how to pull those data elements and merge them with your epidemiologic data. Now, before we move forward, I highly encourage you to go ahead and install the different software that we'll be using. We'll be using the R statistical package. But we wanted to choose something that's freely available. There's no cost. You just have to download it. And it's used not just in geospatial applications, but you may already be using this in public health research or computer science, machine learning kinds of applications. And so it's just a very powerful resource, and it's great to be able to use R to do spatial analysis in addition to the many other great things it can do. So you can actually, it's hard to see, but there's a link here. So if you just click this, it'll open a window in your browser and you can go ahead and download it. RStudio is a shell that you can use to interact with R. It has a lot of really nice features that make it more user friendly. It makes it easy to look at the different data objects you have in storage. It makes it easy to open tables and look at them. It makes it easy to make visualizations and save and store them. And so it's very nice to use R within RStudio. So you can go ahead and download that. Again, if you click your mouse or if you point your mouse over the here, there is a hyperlink there, and you can just click that and download it. The last thing that you're going to need is to request an API key from the US Census. You just have to like enter an email address, and then they'll send you a key. And that you need this key in order to access the different tables in the census that we'll be working with in this tutorial. So our goal today is to learn to install and load R, and specifically to load the packages that are involved in spatial analysis. We want to use the tidycensus package to be able to search for census variables and acquire different census socioeconomic measures and spatial databases. We're going to learn how to compare projections in 2 different databases. We're going to have this ovarian cancer case database and then the census database. And so we need to make sure that those are projected the same way in order to do our spatial joins. We're then going to learn how to make maps using ggplot and tmap, and then we're going to learn to perform basic analyses, do some visualizations, and then export our merged spatially joined data for further analysis in R, in SAS, or some other statistical packages. So the first thing we're going to do is we're going to now move into R. So I'm going to stop sharing this window, and I am going to start sharing my R window. And so this is what the RStudio interface looks like. We have a console down here where you can type commands directly. We have this window up here that is called the script. And so this, if you use Stata, this would be like a do file. In SAS, this would be like a program that you're writing. And so it's nice to just be able to save the steps that you're doing and then be able to edit them and modify them in the future, or to refer back to them in the context of different projects that we're doing. So the way R works is it's a programming language and a functional programming language. And so the way that we use it is we tell R to do different functions and tasks. And so in order for us to leverage the spatial capabilities, we have to load and install packages that other users have written that perform a variety of really cool analytic things. And so you can sort of create a new script by going here to the plus and then hit R script. I've already started one here. And so I've just using the hash, I've created comments, and I've just named this Zhu Center course vector data created by my name, date. And then the first thing we'll do is we'll want to load these different libraries. So SF and raster are used to work with vector and raster data files. SP data has some spatial data sets that one can use to map and kind of test some of these different functions. Read R is used to help with reading in different files in R. Grid, ggplot, and tmap are all used for data visualization and mapping. Mapgam is a package that does some very sophisticated spatial analyses that we won't be that aren't the focus of today's discussion, but has the database of ovarian cancer cases that we'll be using for this exercise. Gtools and Gmodels are used to do various statistical analyses. Grid Extra is used to help with plotting, formatting. Tidyverse has a number of functions that are used for just basic programming and automation and data processing. And then tidycensus and Tigris are used specifically for mapping and spatial data analysis using the census. So now I already have installed these packages. And so what I need to do then is just select these and hit Control Enter, or you can hit Run up here to load the packages. Now, if you haven't yet installed these packages, you'll get an error when you try to run these libraries. And so if you don't already have these loaded, what you'll do, well, I'll just wait for this thing to finish here. What you'll do is you'll type install.packages, and then you'll, in quotes, type in the name of that package. So if I wanted to install SF, I would type in install.packages SF and then run. I'm not going to do that because I already have it. So you'll just have to kind of do that. And in the handout, you can just copy and paste all of those. I already have them there. And so you can do that, install them first. Then once you've installed them, you have to load the library again. And then down here, you'll see some red, but these are all typically warnings. You'll know. You'll see an error message if there's something wrong. So we've loaded our packages. Now we need to read in our spatial data files. First, our ovarian cancer case points file, and then our census CA tracts polygon file. Okay. Before getting started, we want to set a working directory. And so you can do set WD, and then in quotes, you can copy a directory of your choice. I'm going to go to the directory that I'm using. You can find a place on your computer. I encourage you not to just use your desktop because it's easy to have your desktop be a mess and not be able to find anything. I'm going to save it in this folder. And then I'm going to just, this is kind of annoying in R, but you have to change all of these slashes to go the other way. So bear with me for a few seconds as I get that done. Okie dokie. So now that that's done, you're going to see me. I don't use the run. You can hit run. I like to just do control enter. I can put my cursor at the end of a line and hit control enter, and it'll just run that line. So it's a little bit faster. And so now that we've set our directory, we can read in our ovarian cancer file. So to do that, we are going to type in CA data. CA data is an object stored in this mapgam package. So when I do that, you see that this object, this data frame is what it's called, a table or database, tabular database called a data frame, shows up in environment under data. If I click on it, left click on it, I can open the table and I can see the different columns. So I have a column for follow-up time, event, X and Y, age, and insurance. So no surprise, that's kind of what we said there was going to be there. And it looks like it read incorrectly. So now what I got to do is I have to convert this into a points file. So I can just copy it over. So I can use the assignment operator, and here I'm just making a copy of CA data and calling it CA points. I'm then going to convert that CA points into a shape file, into a vector file of points by using st as sf. This function will take in the data object that you want to transform and then coordinates. And you have to tell R what your which columns in your table correspond to the longitude and latitude. Longitude has to go first. In this case, it's X. Latitude has to go second. And it's Y. And these need to be in the right order. Otherwise, as you can imagine, it's going to flip everything and cause problems. So we're going to go ahead and run that. So we have basically 3 copies of the same thing. We see there's one less element here, and that's because the geometry has taken the coordinates, the X and Y, and put it into that field. Now, before recording this video, I tragically had to end my last attempt because I ran out of space in my memory and R was starting to crash. So in order to avoid that from happening again, I'm going to remove my unneeded objects from memory. I'm hoping that's going to help us out later on. And so if I type in RM, CA points, and CA data, those are the 2 objects that we don't need anymore. And I'm going to keep doing that throughout so that we can hopefully avoid having to record this again. So we're going to do that. We now have just one table stored there. It's our points shapefile. We saw that there is a geometry. Another nice thing to do is to type summary CA points SF here. I'm just going to clean that up. I'll put this down at the bottom. And then you can see down below, we have time, event, age, insurance, and geometry. And then we can see this EPSG-NA. So that means that there's no projection currently. And so that's going to be a problem for us because if we want to do a spatial join or if we want to make maps, we need to be able to project it. So we're going to put a pin in that. We'll come back to it and fix that problem. But it's good to just be able to see that we do, in fact, have this. It is treating it like a shape file. It has a geometry assigned. All well and good. I'm also going to save this file just so that I can refer back to it. I encourage you to get in the habit of doing that. So I'm going to say Zhu Center course vector, and then I'm just going to save it. Okay, good. So we have our points data. And now our second step is we want to read in RCA tracts polygon file. And for this, we're going to use the tidycensus package. You're going to need your API key. I'm going to go ahead and copy it. So I'm going to copy and paste it. Looks like there was something funky going on with the quotes, but that's okay. And so I've typed it, and then I've hit Control Enter to run. And so now I've loaded this census API key. What does this allow us to do? It allows us to query and extract different data from the US Census. So we can extract data from the different years, going back to 1980. Typically, for most purposes now, and most of the databases I imagine you'll be working with are probably from 2000 onwards. So we can get data from the 2000 census, the 2010 census, and the 2020 census data are now available, I think, as well. You can also, so for the decennial census, you can use the get decennial function. And for the American Community Survey, which is done every 5 years, if you wanted data from, for example, 2015, you could use the get_ACS function. And to read more about this, I do encourage you to visit Kyle Walker's website and take a look at the link to his textbook down below. So the first thing that we're going to want to do is we're going to want to search the census for SES data. And to do that, we're going to load the data dictionary. I'm going to call it V00, and I can use the load variables function, specify the year I want. There are different census tables, SF3 and SF1. I'm going to use the SF3 here for this example, and I hit Control Enter to run. I see a new table has opened up, this V00. And when I open V00, I now see that there are 16,520 entries where we have a variable name. And so that's how the census knows that's how it organizes it by these different variable names. We have a label, and then we have a concept. And so what we can do then is we can type in things like income. And I can pull up all of the different census variables that have to do with income and then search for something. So for example, household income by gross rent as a percentage, I could use H073001. So this is a nice, this is a useful thing to be able to do to search for different socioeconomic measures that you find interesting. So I've already done that work for us here for this exercise. I've figured out, we had said we wanted median income, home value, and poverty. So I already looked that up for us. So I'm going to create a new object called cens00sf3. I'm going to use the get decennial function. I can specify the state I want, which is California, the geography I want, which is tract. I'm going to use the SF3 table for this. The year I want to be 2000. And then for the variables, I have to list out all the different ones. I'm just going to copy and paste them from the handout to save us some time here. And again, the way that I got these codes is before we recorded this, I went and looked in the V00 file for the different variables that we want. So we do that. And if I select the lines that I want and then I run, I'm going to give it a second to load it. And so it has stored now those different data elements. So let's open this new object, this cens00sf3. So what I'm expecting to see is a table just restricted to California with the different census tracts, and then data for these different variables corresponding to median income, median home value, and the variables we need to calculate percent poverty. So when I open this up, I see that I have the GeoID, which corresponds to the census tract ID, but then when I see the variable, all of these have the same code. So what that means is that this data set is currently structured as what's called long. So we have repeated rows for the different variables and GeoIDs. So that's fine, that we have all the information we need, but for our purposes, we want to transform this table into what's called wide format, where we have one row per census tract ID. So to do that, we can take advantage of the fact that R is a functional programming language and write a function to do that transformation for us. So the way we write functions in R is we specify that it is in fact a function. We indicate how many arguments it's going to have, and then we use these the squirrely brackets to sort of type code in, and that's going to list out the steps that we're going to perform in order to do this this task. So I'm going to call this function make wide. I will take the argument indat, which is a database. I'm going to use this pipe, which in tidyverse sort of allows us to chain together sets of steps. I'm going to use the select function to just keep the variables that I need for this this transformation. And then pivot wider is the name of the function that transforms from long to wide. In order for pivot wider to work, it needs to know what information is getting pulled from the long data file as a column in the wide data file. So names from is going to be that what's going to be the new column header, and then values from is going to be the data that's now going to be stored in those new columns. So just to kind of, well, let's finish this. So that's pivot wider, and then we always want to, our function, we should return the new transformed object. So wide is going to be the new object. That's the long to wide transformation. So what is this going to be doing? So if I go back to send00sf3, we have our GeoIDs. Variable has the variable name, right? So we want H076001. That is, in this case, I can't fully remember, but I think this is like median household income. So we want this H076001 to be the new column, and then we want this value to be stored in it. So variables names from essentially needs to be this variable name, and then values from needs to be the actual value in the long table. Okay, so we've done this make wide. So let's now call, we'll run this make wide function on sends00sf3, and we'll just call this new object sends00sf3 wide. Okay, so if I select all this and run, I now have a new object. We'll see now, so it used to be 28,196. Now it's only 7,000 rows. So that's good. There's about 8,000 census tracts in California. So that all looks good. So if I open this, we see we have our GeoID corresponding to the census tract ID, and we have the 4 census variables with all the values. Great. So at this point, again, to sort of do some cleaning, I'm going to remove the V0. Well, I'll keep the V00 for now. I am going to remove, though, the SF3, that long database. I don't really need that anymore. I just need this wide one. Okay, so then let's just create all my variables. So I want median home value, I want median income, and I want percent poverty. So if I want to figure out what each of these things are, I can go back to the V00 table. And then I can, so if I want to know what, for example, H076001 is, I can just type that into the search. And so that's the median value for specified owner occupied home. So that's probably the home value, right? So that is the home value, actually. So we can, instead of that 07 that we don't know what that is, I'm going to just call that MDHVAL. And what I can do here is I'm going to divide this by 1000. So the reason for that is if I do summary send 0 SF3 wide, let's just do a summary. So summary gives us some summary statistics of the different columns. So we said that this was home value. So it's in it's in dollars, which is fine, but this is just a little hard to read. By scaling it to 1000, it'll just be a little easier to read in tables. And so let's go ahead and do that. So now if I hit the up arrow key, I can call the same, I can repeat something that I typed into the console. And so if I do it again, now we see it's now in thousands. And so that's a little easier to read. Okay, so now we'll do median income. You can also just click to make it easier. And so for median income, it's P077001. Same thing, we'll divide by 1000. And then for percent poverty, here we're going to have to divide two things. And I want to multiply that fraction proportion by 100 to just make it a percentage. And so here, the two elements that we need are 002 and 001. And to just understand why, if I take the P08700 and I put it in here in the search, we see that we have a total. So that's the denominator for this table. And then we have all of these different breakdowns. So we have everybody who was below the poverty level in 1999. And then if you wanted, you could look at different age groups. So the numerator is P0870002. The denominator is the total. Okay, good. So let's go ahead and do that. And now what we want to do, let's just keep the new variables we created and then the GeoID that we need to merge, the census tract ID. Let's try not to make any typos. So if I do this, just want to keep it consistent. So send 00 SF3 underscore F, send 00 SF3 wide. Good to just read through and make sure everything looks good. Okay, so now if I open this send 00 SF3 underscore F, we see there's only 4 variables, 7,049 observation, and lo and behold, we've got variable names that make sense. We've got everything scaled. This looks great. So now we can, again, do some tidying up. Let's just remove the V00. We're not going to use that anymore for now. We can remove the send 00 SF3 wide because we don't need it. We just need SF3 underscore F and CA points SF. So, okay, so we're saving some space. And now we can also run a summary on SF3 to take a look at the summary statistics. So median home value at census tract level in California is about $188,900. Median income in California at census tract level, average census tract is $51,620. And then the median percent poverty, census tract percent poverty is 10.8%. It's okay to see a few missing. The NA, that means that there was no percent poverty calculated for 27 tracts. And that may be because those are not residential census tracts. They may be in business districts. So that's fine if there's a few missing. So good. So we've got our percent poverty and we have a table. But now we need the census tracts shapefile. Right? So we have a table now, but the same way that we had to convert our points table into a shapefile, we have to convert this table of census tract socioeconomic data into a shapefile. So to do that, we're going to use the Tigris package. So we'll type this Tigris use cache, and then we will use the tracts function to read in for California in the year 2000. And then we're going to rename this CTIDFP00 to GeoID because that's how we are going to merge. So we need to merge our shapefile of census tracts to our table with median home value, income, and poverty, percent poverty. So if we do this, it's going to take it a little bit of time. It's a fairly large database. So our shapefile has 7,049 observations. If I do a summary on CA tract shape, we can see here that there's a few other elements. Typically, a lot of these shapefiles will have the FIPS code for state, county, and tract. The GeoID is just all of them combined. And then there's a few other things that typically we don't use. land is the land area, which can be useful for calculating things like population density. But generally, we don't typically need a whole lot of those other things. So, okay, so we have this shapefile. And now what we need to do is we need to join our tract shapefile with our table. And we're going to use GeoID as the merging key variable. And so we're merging our table with the socioeconomic data to our shapefile of census tracts so that they're all in one place. So if I hit Control Enter here, I have this new object, CA tract shape join. And at the end, I have all of my socioeconomic measures merged. I can also look at it by typing summary here. And it looks like everything worked. There's only the 27 missing per percent poverty. So that's good. And now again, we'll do some house cleaning. We can get rid of the shape. Yeah, just that. Oh, and now we don't need the table anymore because we have it merged to the shapefile. So now we just have our point shapefile and our polygon shapefile. So now what we have to do, which is very important, is we need to check our projections. And so the reason that this is very important is, if you recall earlier from our lecture, when we are trying to represent three-dimensional space, the world we live in a two-dimensional plane, there's some distortion that needs to happen. And so these projections are ways for us to do that distortion while preserving some of the relationships, the spatial relationships between the objects that we're studying and are interested in. If we're not careful, when we're taking two different databases, so we have our points epi data and our polygon socioeconomic data, and we don't match the projections, we won't be able to merge them properly. And similar to a tabular database where you haven't sorted in SAS or something, and you get a merge, you get something out, but it's wrong. With our shapefiles, if we don't check our projections and we try to merge, we'll get something out, but it's going to be wrong. So to check our projections, we can use the stcrs command. So if I type st_sr crs and ca tract shape join, I get sort of a bunch of things. I get the NAD 83 CRS, and then I have this EPSG code of 4269. So if I do this for CA points SF, I get an NA. So remember we said that before, that there was no coordinate reference system. So that's going to be a problem. So to resolve it, and the problem is then we can't overlay, right? If we don't even have a coordinate reference system, there's no way for us to know that the points are being drawn in the right place and that they are going to correctly overlay with our polygon file with all the socioeconomic data. So what I have to do is I have to assign a CRS to our points. Now, typically you can sort of make an educated guess for this. So 4326 is a common one for lat and long, or you can refer to the documentation for the database. So that's what I did here. Because our points data come from that simulated ovarian cancer file, I went to the MapGam package documentation, and in your handout, you'll see that there is a CRS that's been found. So I'm going to just copy that, and I'll just paste it here. And then I'll run. And so now if I do stcrs data points SF, it now at least has something, but this EPSG is totally different. So to match the projections, I'm going to take my points file and I'm going to transform the CRS by replacing it with the CRS from CA tract SHP join. So CA points projected. So I'm not overwriting, I'm creating a new projection of my CA points by transforming my original one, by replacing the CRS in the original one with the CRS in the polygon census tract file. So now when I type stcrs for my new object, I see that it's 4269. I see NA D83, like it was for my shape joint. So now I can remove my SF file, and now I have my projected file, and my points file is now projected correctly, and my tract file, they both share the same projection. Now that we've done this, we can go ahead and make some maps. And the maps are also a good way to just check and confirm to ourselves that this actually worked properly. So we'll overlay the socioeconomic data maps with the ovarian cancer case data maps. And so we'll use the ST. So we've used the SD transform to do to get our projections to match. And now what we're going to do is we're going to use the tmap package to correctly overlay, or we're going to use the tmap package to make maps, and we're going to overlay, and we're going to visualize the points and see whether they in fact are in the right place, and they're sort of distributed throughout California like we expect, and we're going to see whether they sit nicely on top of the polygon shapefile. So I can write some code here. I'll call this map overlay. Anytime in tmap we're drawing a map, we have to first use the tm shape function, and then for my polygon file, I'll use tm polygons. I'll say fill, we'll do home value here just to be able to see whether those data are appearing correctly. To generate the scale, I can use this tm scale intervals, and then I can assign colors to those. Different bins. I'll use the red, yellow, blue. I'm then going to specify the legend and the title of that legend. I'm going to call it median home value so we can read it and we sort of remember what it is. And then I'm going to do another tm shape, but this time for my points file. And so I'm just typing some things here. So the shape, this is the size of the shape. We can make it green, and then the size can be 0.1. And these are just different sort of, we want to make it easy to see. And so I've sort of shape equal 2 is going to make them triangles, and then size equal 0.1 is just going to make them kind of small so we can see them. Important to just point out that for this exercise, I'm drawing points on a map. It's usually not a good idea, though, to publish or to include a presentation, a map with points corresponding to actual people's addresses, because it's an unlikely occurrence, but certainly, we probably wouldn't want our own addresses to be sort of presented and just kind of shown to people, right? And because if it's a health study, then you're telling people something about the person who lives there, what their health status is, and it's not very good. So we'll do this. We're kind of mimicking what we might do if we're doing some spatial analysis and we're just trying to check. So I can go ahead and run this and then type overlay. it will take it a few seconds to draw this because it has to draw 7,049 census tracts. So we'll just give it a second. Okay, good. So it drew, you can see very nicely these little green triangles, which are corresponding to the residential addresses of this simulated ovarian cancer cohort. And we can see in colors the median home value underneath. And so there's a lot of cases that we would expect coming from the Bay Area and the LA, San Diego metropolitan areas. Fewer cases distributed in the center of California and towards the east of the state. Cool. And so what I'm going to do again to make sure we don't run into memory issues, now that we've drawn this, we can go ahead and remove it. We can also make maps using ggplot. And so ggplot is if you use R, you probably are familiar with this. ggplot does a lot of different kinds of visualizations, including box plots and scatter plots and heat maps. So it's cool to be able to use it to now make maps as well. To sort of help us do this a bit more efficiently, I'm going to write another function, and it's going to take a database as an argument, a variable as an argument, and then we're going to have a label that is assigned so that we can see it. So if I type in p1 ggplot data equal indat, the input data set AES fill equal invar. So this is basically how we make our map. So invar would be something, as you'll see in a second, like median home value. Indat is CA tract shape join. And then the label will be whatever we want. So AES fill equal invar will allow us to make what's called a chloroplet map. So that's like what we're seeing here, where there's a color that's sort of the average income, for example, in different census tracts in California. So once we have that written, we can assign a few different things. So geom sf color equal na. So this is telling us that we're reading in a geom sf object and making a map. The color is na because we're going to assign color in this next argument, the scale fill. Viridis is a nice colorblind color scheme to use that makes it easy to see differences in different geographic areas. Here I'm specifying the title. And for theme, you can set the size and the title. So I'm going to use 6 here. Just to make it a little easier to see. So here we can make the legend size a bit bigger. And then, as we said, we always want to return that object so that we can use it and store it in something else. So we've written this function to make a map in ggplot. So let's run this, and then we can then call that function. We'll read in CA tract shape join, specify the variable name, and then specify the label. And I'm going to now just copy paste. I want to make maps for each of the different variables that we're working with. We had median income, we had percent poverty, so now if I just run this, we've got all of them saved. If I want to see what one of them looks like, I can just type P1, give it a second to draw. So now we see median home value, we can see all the different colors. And what's nice about this is actually there's no borders, so you can see the variation even in the urban areas where there's a lot of change. Now, if I want to make a panel, I can use grid.arrange, specify the different objects I want to plot. So this will arrange it as a 2x2 matrix. Let's give ourselves a bit more space here so that we can see. And then can hit Control Enter and just let it draw. This usually will take it a little bit of time because it has to basically make all the plots and then it has to draw them. So hopefully it'll start to draw in a little bit. Okay, yeah, you just have to be a little patient. So we can see formatting is a little wonky in the bottom, but we do see the maps. We can see very clearly how higher income is really concentrated in the metropolitan areas around the Bay Area, LA, San Diego. Um, Income is a little bit distributed a bit more, and then percent poverty is highest in the Central Valley. So that's nice that we can do that. I'm going to now clear up some space, and so again, we'll remove some of these objects that are taking up a lot of space. Just removing them also, it's not easy. Takes a little time, takes some time to draw and also takes some time to remove, but I think that that'll be for the best. Just give it a second. Okay, there. So that's been removed. So now we'll do a panel with tmap. And so here, our syntax is a little different. We will use the tm shape first, then polygons, specify what we want to draw. We'll use fill.scale to specify the colors that we want. And then fill.legend to give us a title. So here, instead of writing a function, I'm going to be lazy and I'm just going to copy paste. Let's just make sure I've typed everything correctly. TM polygons, fill.scale, fill.legend, TM scale intervals, TM legend, title. Well, one way to do this is just run it and then see if it draws properly. And TMAP does take a little time to draw, so we'll have to just give it a second. Okay, so yeah, so that worked. But here we can see that these borders are all like the gray is just kind of wiping out any. It was easier to see what was going on in the city is using ggplot. Um, but this is just another way to draw these. So what I'm going to do now is I'll play around with this a bit so we can see some other things. So we'll do the same thing. We will make maps of median income and percent poverty. It'd be nice to change the colors around a bit so you can use our color brewer and palette to kind of pick colors that you like. I'm just gonna try a few different ones here. And then to do the panel, we can use tmap arrange. And then at the end, we can remove these to clear some space. But so we've run P5, so we'll do P6, P7, and then we'll use tmap arrange down here. Let's just give ourselves a bit of room. It's good practice to save. Let's see if it'll. It seems like it's thinking because it's not saving, but it's okay. Just run. So this will take it a little bit of time. So you just got to be patient. Okay. Wait for it to draw the others. what's nice is TMAP has evolved actually since we first started the course. And so what happened sometimes was that these legends would pop up inside the panel with the map. And so it would be hard. Sometimes it would cut into the map or the legend would sort of cover parts of the map. And it was kind of a pain to be able to get both of them big enough so you could see what was going on. And so this format is a little bit nicer. And this is, I think, TMAP 4. So also when you're installing packages, it's good to be careful to see which version of TMAP you're using because you may be using an older version. And if you are, it's fine. I think everything will work. It'll just look a little bit different. All right. So we're able to draw everything. So similar information as before, slightly different format. So you can choose whichever one of these you think looks nicer. And so two different ways to do panel maps. Great. So I'm gonna clear my memory here so that we have space. And now, if you recall, the whole purpose of doing this, maps are fun, but the purpose of this was so that we could see whether we could correlate measures from the census with measures in our ovarian cancer cohort. So to do that, we need to do what's called a spatial join. And this is actually fairly straightforward. We use the st_join function. I'm going to give ourselves some space here so we can see. We are going to join our points file with our tracts file. And specifically, we are going to indicate which columns we want. So we're first, and what I'm going to do is I will take to overwrite and add these columns, I will just copy paste CA points join. So first we're going to append the column with median income to CA points joined. Then we're going to append the median home value column. And then lastly, we'll append the percent poverty. Okay, so let's save and run. So again, this can take some time because it has to count 5,000 different points and then 7,000 different tracts and assign everything. So we've just got to be patient, but it'll work. So one thing that we saw there, sometimes what's actually taking a long time isn't running. It's when you have very complex plots, because it has to draw all of these things, that can make R a little slow. So I'm wondering maybe we just switch to a different window down here for the moment so that it doesn't have to keep redrawing everything. So we've finished our join. So if we look at CA points joined, we see that we have all of our original ovarian cancer cohort variables, but also median income, home value, poverty. So that all looks good. Now, if we want to do some analysis, this is probably stuff you guys already know how to do, but one way that we could do that is we could create a indicator for death. We can create a factor variable, specify the levels, which are 0 and 1 in our event variable, and then we will replace them with labels of alive and dead. And then we can make a few plots. And we're just going to make some box plots to be able to visualize this. So we can say X and Y. So what this is going to do is it's going to show us if the median census tract income is the same or different among those who are dead versus those who are alive. And we can do this again for our different. Do it for home value, poverty, and then remember we can use grid arrange to look at these. So let's run. Go to plots. Okay, so this is a little hard to see. So yeah, and then if we want to maybe look at this. Different orientation. This makes it a little easier to see. Okay, so basically the eyeball test, it looks like the distribution of census tract median income, home value, and percent poverty is fairly similar regardless of whether the person was alive or dead. So that means that there's probably not a statistical correlation between these two things. So that's kind of a fun little thing to do. You could again play around with functions if you wanted to automate making these plots. The map, tmap, same idea. You guys can use the code that we wrote for the ggplot to sort of automate that and write functions. And the last step is export. So we can export data to a CSV to use in another program like Stata or SAS. And so we can then, first, we want to drop our geometry column. We have to specify what we're doing. So we want to drop our geometry column, and we want to drop that column from CA points joined, right? That's our final thing. So now if I open CA points joined, oh, sorry, we dropped it from CA points joined and saved it as CA points export. CA points export no longer has a geometry column. And then we can use write.csv points export. And then so if you recall, we had already set a working directory up above. And so I think if you can just write, if you've done that, you can just write in whatever you want this thing to be named. So if I say CA points export.csv and do write.csv, it should appear in that directory that I specified above. If I wanted to be explicit, I could just copy whatever path I want, go to this, and then just copy paste it and add that backslash, and it would get you the same place. And so you can't see, but I'm going to go ahead and check to make sure that that worked properly. So if I go to that folder, yeah, I see it in yep, I've got it here. So if I stop sharing, just show, I've got the CA points export there. So great. We can go back to our handout, and so that's kind of it. So we've learned to do a few things today. We've learned to load packages in R. We've learned to do some pull data from the census, the U.S. Census. We've learned to make shape files and to map those shape files. And then we've learned to do a spatial join with our epi data and our census data using the points to polygon spatial join. And so there's a lot of really great resources. You can go to these online books. The links are all here in your handout. And then there's other data sources that you can use and refer to. The Integrated Public Use Microdata Series has a lot of GIS data from the census and other resources. The demographic and health surveys are for international relative to the U.S., I suppose, for countries in Africa, Latin America, Europe, Asia. There's a lot of really great spatial data there. The Earth Engine Data Catalog is run by Google and has a lot of satellite image data, and they're starting to pull in other interesting data sources. And then Kyle Walker's tidycensus book, highly recommend taking a look at that. So with that, that's it for today's lecture. Thanks for listening, and you'll see me again soon, I suppose.